Now, I don't want you to work this out. What I want you to do is think about, in an exam, what would be the steps you would go through in order to answer this question. So before you even start writing anything, what steps would you need to go through? Now, I am hoping that the very first step would be to try and identify the type of distribution. Because let's take our Poisson conditions that are below this one. So, Poisson is a constant rate of outcome. But there is also a limit. There's only 1,825 employees. We can't get more than that. Doesn't seem to match very well to the Poisson. But our binomial, however, is there a fixed number of trials? Yeah. In fact, there's a lot of them. There's our n. N is 1,825. What's the probability of success? Well, the success is having a day off, and there are normally 365 days in a year. So the chance of any one day being taken off is going to be 1 out of 365. So this matches our binomial distribution. But we do have one issue. Because our n is extremely large, and in our tables there's 30, n is 25, n is 50. Oh, there's no n is 1,825. Shucks. Well, as luck would have it, that brings us to today's topic, which is approximating the binomial with the Poisson distribution. Let's compare our two conditions. So in binomial, we have a fixed number of trials and some chance of success. Now in Poisson, we have our lambda instead. Our lambda is our constant rate, and we know our lambda comes from our mean. So with binomial, our mean is n times p. So when we approximate, our lambda comes from n times p. We're linking up the two means. In binomial, each trial is a success or a failure. In Poisson, we've got natural numbers. Trials are independent in binomial. Again, trials are random and independent in Poisson. So both have this independent random element to them. The big difference though, in Poisson there is no theoretical limit to our number of trials, whereas as we know in the binomial we have an n, which is definitely a limit. So to approximate fairly, we need an n so large, so big, that it basically acts as an infinite sample. I mean, you've probably seen in Poisson where things like fishing from the ocean, yes, there's a theoretical limit of fish you can catch, but in reality there's so many of them that we can use, we say it's theoretically limitless. So for binomial, all we want is a particularly large n. And talking of particularly large n's, I have here a selection of binomial distributions. Each one has an n value of 100, which is quite large, and each one has a different probability. I want you now to copy this down and calculate our mean and variance for each one. So you should have got something a little like this. Here, our mean is going to be 60, and our variance is going to be 100 times 0.6 times 0.4, which is 24. Remember, in the Poisson, our lambda is not only our mean, it is also our variance. So we're looking for numbers where our mean and variance are pretty much the same. This one here with a mean of 30 and a variance of 21, and this one has a mean of 1 and a variance of 0.99. And that is pretty much the same and good enough for us. So you can see, even if the n is large, to be a good approximation, we also need a particularly small p to go with it. Now you might say to me, wow, what counts as a large n and a small p? And I would say to you, no one really knows. There's no exact definition. What we do say as a rough guide is we want n times p to be less than or equal to 10, so our mean to be less than or equal to 10, much like it is here and not there. There's a reason for this, a very practical reason. In our tables, the Poisson stops where the mean is 10. Yes, so let's go back to our starting question. Hello, here it is, our business with the days off. Now, let's have a look at this. So this was a binomial distribution. So we're using a binomial with an n of 1,825 and a p of 1/365. As a little side note, here we go, let's see, our EX, our mean, is n times p, which is 1,825 times 1/365, which comes to 5, which is less than or equal to 10. And our variance is NPQ. We've already got NP. NP is 5, and our Q is chance of failure, which is 364/365, which gives us 4.936. So you can see that our variance and our mean are roughly the same. Now you don't have to do this in an exam every single time to prove that using the Poisson is okay. All we need to say is that because n is large and p is small, we can approximate with the Poisson. And you do have to write that down. You do have to tell whoever's reading your work that you know it's a suitable approximation. Use the Poisson as an approximation. I've already seen that our mean is 5, so a lambda is going to be 5. We want the chance that at least 8 are asking to take a day off. So the people with days off should be bigger than or at least, so equal to 8. Quick number line, because that's not in our books. Remember, the books only do less than or equal to, so 5, 6, 7, 8, 9. We want bigger than or equal to 8, which is the same as 1 minus the chance that x is less than or equal to 7, which in our table, we look it up, will give you 1 minus 0.8666. So the probability that x is bigger than or equal to 8 is approximately 0.1334. And that is good enough for us. Now, sometimes we can still use this if n is really large. Not n, p. P is really large. N is always large, but p is large as well as n. In those circumstances, we can use what is called the complementary random variable. So rather than looking at the chance of success, we look at the complementary to that, which is the chance of failure. So let's take an example where you've got a very large n and a very large p. Now, normally you'd work out the mean and variance. And 100 times 0.99, so the mean is 99, and then that chance times the chance of failure, which is 0.01, gives us a variance of 0.99. Now here, the mean and variance are miles apart. So instead, let's look at the complementary, the chance of failure. And in that case, our chance of failure is 0.01. Now, our mean is 100 times 0.01, which is going to be 1. And our variance is 100 times 0.01 times 0.99, which is 0.99. Now, they're almost exactly the same, and we can use our Poisson approximation by using the complementary. Ooh, Cadbury's Rose is my favourite. So 99% of all Cadbury's Roses are perfect. What is the chance that more than 495 of the next 500 are also perfectly delicious? Now, we've got a fixed number of trials, 500. We've got a P of 99%. So the binomial, X is binomial, the 500 trials, and a 0.99 chance of success. The complementary to that, that's where X is perfect chocolates. Now, we use a complementary, still have 500 trials, but now we're looking at not so great chocolates. So why are not perfect chocolates? This is where number lines are ridiculously useful. So let's look at our original scenario. Looking at having 495, so you wanted to know that if more than 495 were perfect. So 494, 495, 496, 497, 498, 99, 500. So more than 495. So it's not including 495, so it's 496 upwards. You want to know what's the chance that we get 496, 497, etc. perfect chocolates out. Are complementary. Make it a double number line. If there are 500 perfect chocolates, then there are 0 that are not perfect. If there's 499 perfect chocolates, there is 1 that is not perfect, and so on, working backwards. So I'm writing a reverse number line, starting at 0. So I'm looking at this same area. So, more than 495 perfect chocolates is the same as having 4 or less not perfect chocolates. So why? Because n is large, p is small, so stating again why our conditions here. 500 times 0.01 is 5, so that is approximately 0.4405. So we can say that the probability that x is bigger than 495 is roughly 0.4405.